All right, so recording starts. There won't be much going on there for a sec, because first day we get the syllabus. You know, we could wait for the syllabus day for two. Yeah. Um, anyway, so I think most of you know me. I'm Dr. Keith Schubert. I'm a graduate program director here. Can you grab the syllabus from the back corner? Thank you, Tommy. So this is advanced visual logic. So this is one of those kind of fun courses. If you notice there was no book for this, that's because there's no book for this. Because there's really no good, please make sure you bring up the syllabus back over. Thank you. Um, there's no, like, almost every university has this course and it slightly varies what the content is. There are books on the topics, but I have to bring you three completely different books, which would cost you like $600-700. And I think that's stupid, but like a number of the topics are like 2-3 weeks long. So we have three group areas we'll be going through. Advanced digital logic understands the advanced stuff over digital logic, and this is part of that challenge. What you cover in this course depends on what you covered in the first course. Okay? And some people put different pieces together. It kind of depends on what book you used for your first course in this. Anyway, so the book that we had, if you still have your digital logic book, which is actually a pretty readable book, so that is not something easily said in engineering. Most of them are really great sleeping aids. It actually, barely speaking, a decent book. It's got good examples. Some of the appendices are actually helpful, and some of the later chapters are helpful because I am basing it off of what you took at Baylor, which means you'll have the distribution that is based off that book. And we often don't cover the last couple chapters that goes into async and things of that sort. Right? We usually also leave some basically the logic family builds and things like that. We don't cover those ones. They're later chapter stuff, and it's important you get the foundational ones. And that's actually, in my opinion, the right way to go with them. Some people start with the designs on how the logic families are made. You're going to go through that. That's one of the topics we're going to talk about. But the average person doesn't need to. They need to know how to assemble logic in general. That's the more common topic. You're getting into the next level of specialization. So this course, I said there's three topics, but I might put it in two big areas. There's going to be one that's kind of like more in-depth on the theory side, and one that's going to be on more on the practice side. First half, we're going to do theory. Second half, we're going to do practice. The theory section has two pieces. One is going to be these hardware components. And since I know all of you were craving this over summer, we'll start off with some quantum physics. We'll probably on that one. So quantum physics can actually be a lot of fun, but that's actually one of the topics we're going to talk about, and how are transistors made and all the rest of this. You've probably seen some of this in other courses, and they're often interested in calculating these. We don't necessarily care as much about that. If you go really far into this, you'll be doping semiconductors, for fabrication purposes. Now you're going to start caring about it, but we don't care about that at this point. Right? But what you do care about is understanding how and why it works. Because I have heard and seen so many things out there where people get a couple facts right and their reasoning is really garbage. So I want you to have good reasoning to understand why things work. And so that's part of what we're going to cover here. And then we'll go into basically how to analyze some of these logic families, know what they're good at, how they work, how you can see functioning, things of that sort. And then we'll go into the next part of this, which will go into some advanced techniques and then asynchronous. But we'll talk about, how we can take some of those techniques you learned in your first course, K-maps and all the rest of that, which are cool, they're good visualization, but how do you really do that? Right? I mean, it works great for like 6 variables, but what do you do when you've got like 32-bit variables and you got multiple of them? I mean, K-maps really kind of fall apart when you got like 100 and something variables. It's really kind of hard to draw that. So there are extensions of this, right? There's an algebraic version on Kluski you'll see later on that unfortunately is NP complete. So we'll have to move into what do we do with that. Then there's espresso, which kind of is a heuristic that works fairly well, but it can lock up in places, things of that sort. So if you look on the schedule here, you'll see some of these names in here. And then the other thing we've done is, I mentioned the asynchronous. So far, all of our logic to prevent problems has been synchronous, because we can avoid errors and things of this sort by using timing to basically wait till all the possibility of errors are gone and things have settled and then clock it. Unfortunately, that's slow. So what happens if you need something fast or something that can react intersample? Now you're in asynchronous land. So how do you make sure that circuit doesn't blow up on you when you no longer have protections? And special things happen. So we'll talk about some of those basic techniques. All right, so that's kind of what we're going to do. Then interfacing and things of that sort. Then we move on the second half to more practical stuff. We're going to go into system Verilog and talk more in detail some advanced techniques, generators, things of that sort. How do you extend those into higher dimensional areas to solve big problems? And we'll tackle things like right now you've got like adders where you did like triple carry and things of that sort, but those are slow. So how do you actually solve this in different trade-offs, right? Then we'll get some complexity and things of that sort, and how do we build things in that way. So you'll see we're going to do carry look ahead, we'll do conditional sum, things of this sort, which allow you to do trade-offs between time-based complexity to be able to get a circuit that will meet your needs. And then we'll eventually move up to average difference engines, which is kind of like since we're starting kind of at this very low level, you open up to build a simple early computer. This is 1800s type stuff, but it's surprisingly useful. And it's useful in the fact that it kind of starts with the equations you're going on. So even though it's an old machine, sometimes you'll build one of these that has a simulation part on it, because they're actually fairly efficient for doing certain types of predictions and running equations and things. So it gives another kind of tool in your toolbox. So that's big level. What are we planning to do this semester? Um, Now, you'll notice there is still readings, and the majority of them say K. That's because I've got some online notes. Since I didn't want you to buy them over the last 20 years, I've been kind of building out notes that I can keep everywhere. Okay? So, silly thing, but whatever. Um, and those are basically the chapters we're going to go through. When it is L, there's a lab manual, but that's for that practical areas. So that kind of just gives you those two things. So one is my online thing. It is inside of our um, uh, Canvas page and things of that sort, which I opened up this morning. And L will release later. I'm still working. There's always typos in there. I am dyslexic. So I'm always trying to find little typos. In short, if when you're looking at any of these, you're like, man, something's hard to understand, or it's hard to read, or anything of that sort, please just tell me. It doesn't bother me in the least. I'm trying to read something that's useful to you. So you are one of those. You'll notice under the homework category, there's two types. The first half says homework, and the second half says labs. Lab is a loose term since we don't have a second lab, it'll be a bit here. But practical stuff, like I have to distinguish between things like a Canvas quiz, that's what we're doing for the homework, which is just checking basic knowledge to understand these here's, intrinsic and extrinsic ones, and here's a circuit, and the analysis and things of that sort. That's kind of homework problems. So those will be Canvas quizzes. When I get to the lab, we're going to do stuff in class. We'll talk about the theory, and we'll start building it, and then you'll finish it in your own time. And you'll turn in reports for each of those as you're building these kind of major circuit areas to learn how to do these techniques. and then you'll turn in a report on those. So that's the distinguishment on the homework versus lab in the homework category. So far, so good. Uh, I'm trying to get through this relatively quickly because we actually have a lot of stuff to cover. My office, 304B, and also the brick, I didn't list that one. I figured, originally I figured most people would be here on campus, but I noticed there were mostly grad students in here. So the brick might be easier to hunt me down. But my office hours, that is, okay, yeah. So Tuesday, Thursday, right, after class till partway through lunch, basically. I'm also available at tons of other times, so just let me know when it is. Those are ones I will make sure I am in my office and things like that. So, but if you're like, oh my gosh, I have a class right after this and this doesn't work, then just email me when you all talk to me and we'll figure some time out. Then, anything to objective. So I mentioned everything that's in there is basically, it gets into some of the details, but it's on the top part. So I'm not worried about a catalog description again. Most of those are really more for ABAT, because all that information is really in the catalog, but it's on the other sheet. But we're coming up to an ABAT accreditation next year, so you gotta make sure you've got all the stuff that makes ABAT warm and fuzzy. So grading, if you haven't had me before, the scale is right there. I don't believe in curving anything. I know a lot of people believe in curving. I do not believe in curving. Curving essentially means you don't need to know things as much and you still get your grade for it. I'm a personal believer in if you want the grade, let you earn whatever you want for the grade. So anytime you get something wrong, I will allow you to make those points up, but you have to do something that causes you to learn to get it. So it's, in one sense, better than curving because if you didn't get it right the first time and you missed a whole bunch of points, you'll be on the bottom of the curve. On here, if you're willing to put in the effort, and you learn it, I'll give you whatever grade you're willing to earn. So my point is, I want you to know. I don't care how you know it, when you know it, I care that you know it. The thing of this is, please don't use stuff to bypass things, right? There's a lot of ways that you can get stuff that doesn't increase what you know. It just gets something that looks like a reproducible output. You can find stuff online. You can, there's a lot of AI help. There's borrowing stuff from neighbors. There are a million ways. Some of them I can find, and let's be honest, some of them I ain't got to be so great at finding. But I would say this, you're literally, if you do that, stealing from yourself. You're going to Baylor because we're going to give you a good education, and you get a lot of interaction to ask questions to learn. Why get that and then steal right out of your own head the knowledge? Right? You want a grade, I get it. Helps you to go on for whatever else you're interested in, looks good when you're talking to employers, and I'm willing to let you learn it. Just do it by learning. Most of the ways you can do it, like if you do stuff on homework, then you can do tutorials. I essentially write a tutorial to teach yourself how to solve the problem. I say write kind of loosely. You can do this as a video, whatever. I don't care, but you should use several basic steps. And you're welcome to talk to me about these before. But these are kind of the process. How would you learn anything? Recognize what you did wrong and just admit it. This is one of the toughest things for people to admit they were wrong. But you can't learn unless you admit you were something. That's how your brain triggers, this was not the right way and pull things the right way. So admit what you were wrong, identify how you thought about it wrong, so you can kind of see the wrong path, then say what the right path is, and give an example. Simple. Right? Explain your steps when you're giving your example and things of that sort. But if you do that, I know you know it. I know you know where the error was, so you won't do that again. I give you all your points back if you do that right. If it's on a lab one and it's identified, just fix it in the lab and submit a new one. But don't try to just do the minimums. Do what you need to do to understand it and convey it. Okay? Again, nobody's going to see this outside here, so use this opportunity to really figure it out. And if you're looking and you're like, I think I need to do something, I'm not really sure, so that you make sure you know it. The goal is for you to learn, then we get some evidence that can prove you learned, and we give you the grade. Simple enough. Right? So earn what you want. I do recommend you read, even though it's just kind of online stuff. It's really short in most of my section areas. You will find in some areas you're like, oh, I wish you describe this more, so you should tell me that. Some of it we'll talk in here, but let me know. You'll see the percentages. So can somebody do me a favor and add up all the percentages? Yeah, what's going on with that? Clearly, I didn't. Okay. Well, let me just point out to you that I knew this was the case. So there's a reason for this, uh, which is the other accrediting body, the one that accredits the whole university. Make sure graduate students cannot take a course with undergrad and be evaluated identically. So you'll notice there's one section here that says project and it's 20%. If you were an undergrad, you don't do that. That's why the first thing in there bold is grad students only. So this is one of the big ways to make a differentiation between undergrads and grads. But I don't just want it to be arbitrary. So for grad students, you're doing something practical as a research area. Let's figure out how to do something in this class that will help make a project and away we go. Or something that'd be really interesting, that'd be helpful to you get a job later. That'd be another good way to do it. Or you just find it interesting. Let's face it, it's interesting. Right? I mean, embrace your inner geek, right? We're all in engineering. We can't deny reads. I'm proud of it. That just means you're smart. So, maybe there's just something that's fascinating to you. You want to try. That's a great way to do it. But let's find something in there. You'll do the project. It'll be lab size, but you're a lead. You're picking what it is. It's something neat. You do it on your own. You write it up. You call it a project. It's now 120, which means all those percentages will be multiplied by 100 over 120 to rescale them, which is basically 5 steps. So we just finally scale. Conveniently, I can enter the percentages like this right in the canvas and it'll weigh it. And if you're an undergrad, if I put no grade in that 20%, it just keeps the other way. It doesn't treat it as zero. I've got it any unknown grades are just ignored. So it'll just ignore that whole section for you. Okay. So conveniently for grad students, if you don't put a zero there, that really does count as same. But if you put no grade in, it's the student in the path that has, so if it's a weird passage through something, it should just work nicely that for the undergrads, that it just flows through and everything's good. So most of these are kind of standard statements, and I don't think most people are going to remember them anyway, so just look them up if you need them, they're also. Then there is from 10 on down, this is what I call legally. These are the amplifier junk that I have to say, well, it's not all junk. I mean, actually, most of it's very good stuff, to be honest with you. But you've probably seen this in 1,000 places, but we kind of, by academic integrity. I've got to talk about from my perspective anyway. Right? Treat this like you actually respect yourself and your peers. Right? That's how we want to do it. So one of the biggest things is when people steal your stuff, you can get more stuff. When you steal your head, that's to me a much more fundamental violation of who you are as a person. So stealing knowledge, so if you give somebody an answer, you're stealing from their knowledge. Now that doesn't mean I don't want you to work together. I'm thrilled if you work together. Just don't give answers. Give techniques to get the answers. Discussing how do we go about doing this, that person learns from giving an answer. It's kind of like when you teach somebody to cook a meal or you just hand them a meal. somebody hands you a meal, you eat the meal, you move on, and you're like, oh, that was tasty, but you don't really know how the whole thing worked. Somebody shows you how to make it, you still get tasty, but you don't really know how to cook for yourself. So just think when you're cooking together, don't just have solutions, methods to get solutions, right? Somebody's confused on something, look it over. Because that process of debugging is going to help you tremendously. When you go out and work, whether it's in industry or academia or whatever you happen to go into, at some point you're going to move up where you're supervising people. They're going to have problems. They're going to own them, right? And if you know how to debug stuff, you're going to be useful. You can look through stuff and say, hey, something's BS to you. And B, you can also look through somebody's not they're just confused and you can help them through that process. Right? It is a tremendously useful skill. So, good stuff. And academic success, this is actually pretty important thing. So I just want you to know some here. If you need accommodations, like I'm dyslexic, no problem admitting this. Right? You know, there are different ways minds think. Don't feel bad if you happen to have any of these different ways of thinking. If you need accommodations, the only way I can give them though is if you talk to all. So if you need different times or other stuff, like for instance, there's going to be a final. I generally, it doesn't always make sense in advanced courses, but it does in this because there are some material that's just amenable to it. So we will have a final. And if you want to be able to have extra time or things of that sort, you gotta let me know an alternate testing spot. The only way I can know that is through hold on. Legally not allowed to make accommodations without that. So if you do need help, right, Success Center or Writing Center, things of that sort. Right now there is an artificial intelligence statement in here because AI is growing and yay, large language models, the world's changing. Right? Everybody gets thrown on these. I encourage you to think of it like this. Right? AI is actually a pretty useful tool to publish your work. Please don't use it to do your work. If you trust it to do your work, 9 times out of 10 it's going to be fairly nice. But if you let it do the first edit and you don't ever recheck it afterwards, you're probably going to get garbage. There are some strategic holes that AI is going to have. And yes, they'll tell you we'll patch those holes, and they will patch those holes. But it's a waterbed effect. You push one hole down, it's going to pop up somewhere else. Right? An AI model is not going to ever become you. Right? So you are the only thing that can really achieve that. Now, it can help you. You can put the basic idea sketch and you can ask it, hey, rephrase this. It'll fit with your basic knowledge at that point and just kind of put it in a prettier form. Great at that, totally fine with me. Just that you start with your knowledge, use it to polish it, and then reread it because sometimes it does do stupid things. Right? This is just reality. Right? So I know it's popular starting things off and whatever with it, but I encourage you not to. Part of the reason is it will make it difficult for you to develop arguments. So if you don't learn to start the writing yourself, when you have to make a an oral argument in people, you won't have that same logic process to generate the argument. So therefore you'll sound sad. If you learn to write it at least first and then ask for polishing, you'll be able to form the argument better when you need to convince somebody of something in kind of a one-on-one. So that's why I actually care about it. There is a good reason for it, right? That's a you benefiting reason. So I'm not stopping AI, I'm just saying use it in a way that will help you, not the way that it'll hinder you. Make sense? Other than that, climate change and community, be cool to each other. I understand that for some people this is going to be near the graduation. So if you do have job interviews or things like that, they're going to call you. You know, just please, if they're calling you, just quietly step out. Don't just be kind to everybody else in the process, right? If you're showing up here, be cool. It does deeply bother me when people are stroking other sites when I'm here. That basically says I'm not important or what I'm saying doesn't matter. And I really do think a lot and have about how to present this to you and give you exactly what you need. So please do not go other places. If you deeply feel that some YouTube video or whatever else you want to pursue is the right course of action for you at this moment, you don't have to come. Nobody's holding a gun, and I don't take attendance. If you think you can pick it up without it, I think you're wrong, but hey, good luck. Okay. So just be cool on those areas. If you're here, be here. Right? Um, if there's a crisis situation, please take care of it. The general sexuality, personal misconduct, civil rights, that's a pretty general statement. And as long as you're following basic ethics, treat people well. Right? As Kant would say, treat people as end results of themselves. Right? Not as a means to an end for yourself, or however you want to think about it in Christian things, made in the image of God. Treat people with that high level of respect. You'll follow all these things without any trouble. If you do run into a thing, I am happy to do whatever I can to help you to make these things right. Just know I am a mandatory reporter. That's required by the state of Texas. I actually will lose my ability to be a professor and an engineer if I don't report. It is state law. So, I am happy to help, just know that situation. If you're a first-gen student, military, anything of that, we're happy to give you extra stuff and help however we can. There's contacts, student well-being, health, things of that sort. If you have any particular religious holidays you have to follow, please tell me in advance so I can accommodate early. And the rest of this is just kind of information on food insecurity, addictions, telehealth, just where you can get resources generically. They asked us to include that. So everybody knows where they can get them. All right. Cool. So I can keep it in under half an hour. Are there any questions? No? Awesome. So, I know this is the most fascinating thing. Yeah.
I had a question about the project equipment, if you did on the calendar, I would schedule those outdated.
So if you go on to the canvas, then we'll show you. But it's essentially at that end. I'm thinking to the very end of the stuff. I suggest you don't put it in at the very, very end because it'll block your study for the final. But I'm flexible on what that is. We'll build it, and my goal will be for people who have to do that to the grad students. I'd like to meet early in the semester, and we can start kind of talking about what might be interesting type of projects. So just try somewhere in there to schedule some time to come visit, then we'll sit down, we'll talk about what it is, and we can kind of sketch out to make sure you get something that's very useful. Any other questions? So you'll notice that I did put the full schedule on the front here. That's probably the majority of what you're going to care about. Please do look and think about it. So one other little reason on why to look at it, even if it's not the biggest note, if you look it over and you kind of have an idea of what's happening, when you come in and I'm talking on that topic, having seen it once, A, you'll pick it up quicker, but B, you'll know what was confusing, so you can understand it quickly. So when I was going through, I found that to work much better for retention of ideas. Any other questions? We can move on to some fun stuff. Yeah, not that it's not fascinating reading such things, but yeah, that's not fascinating reading such things. I agree. All right. Paper's a little creased. Okay, let's start with blue one. So I wasn't kidding about we were going to talk a little about quantum. Today we want to really kind of overview diodes and transistors and basically how they function in this. Is everybody basically familiar with diodes and transistors? So what's a diode? Walking down the street, someone comes up and says, "Hey, I'm a diode." I don't know if they're right. I just say if you're lying to me, you're gonna diode.
One and clock for it.
One or two what?
It allows only one way to clock for it.
Yes. So it's going to allow directional current. This is a good functional way of thinking, right? What else do we know about diodes?
Current is take that is roughly 0.7 volts of power to a voltage.
Okay. Why 0.7? Is that every diode takes 0.7?
That is not every dot, that is just an average, I believe. Or at least, that is ideal diode.
So any diode should have that ideally. Yeah. So some are saying that why not? You're right.
That could have a zero.
So here's the fun thing, right? There is going to be a difference. It depends on the material it's made of. So zero point 0.7 is the most common, but that's because it's silicon. So silicon is going to give you about a 0.7 voltage drop. But like germanium will give you 0.3. It's further down the chart, right? It's the next one, the next row down, right? And you can make other ones too. Right? So what the drop is, we can actually make, like your semiconductor doesn't even have to be a element. We can actually, make a molecule that has that net same property. That's going to have 4 outer bonding electrons, which is what we kind of need for a semiconductor. But we can take one from column 3 and something from column 5 and bond them together, and it's going to kind of function like a column 4 in some sense, just as a molecule. Right? Some of them work well, some of them don't. But you can actually make these combinations, and you're trying to adjust. We're going to talk about this in a bit of detail, but it'll have to do with kind of the differences between the electron's energy levels, where it can take them. Right? So it's a great thing, and I totally agree. Right? If you remember the number for it, remember 0.7, because almost everything is silicon. But just remember, it's actually the material. So you can run into other stuff. Sometimes we need those other stuff for different situations. Also, those are good things. Anything else we can think of? Those are the things they do and kind of things about them. Right? Does anybody know what a diode is? How do you make a diode? What's it made up of?
Different types of material put
It
together.
is two different, right? Do you know what those two are?
Either one N type and P type.
So a P-type and an N-type material. So that's some of the stuff we're going to get, right? It's technically speaking, it's made up of a PN junction. And this is going to be important when we go to transistors. We're going to have the same junctions. You're just going to have 3 of them in a transistor instead of the, 3 different regions as opposed to the 2 regions. So we'll either have NPN or PNP. That's not just in a BJT, by the way. Right? That same basic format of, 3 of these regions will be in both FETs as well as BJTs. It's going to be dependent on to be controlled by current or do you allow them to be controlled by field on how these transitions make. Okay. So that's why this is kind of important stuff. So that's one of the big things we want to talk about today. And that's why to understand why this is true, like right now, most of you have facts about them. But how do you know you're right? If all you've got is facts, then it depends how good was your source. I want to get you to at least a good level of understanding. So we're going to talk about the ideas of quantum mechanics. I'm not going to do a lot of calculations because I don't need the calculations. But I want you to have the intuition. This is the important stuff about understand what these are. and will draw the understanding of what the basic principles of quantum mechanics, and we'll actually be able to derive all the properties you want. And this is really important to us. Like, have you ever heard of valence bands and conduction bands? Well, how are they bands? I thought they were finite energy levels. Okay. Then it gets into some weird stuff. We're going to remove that uncertainty. You will know exactly why there are bands by the time we're done today. So that's what I want to get you to today. And if we have some time, I'd like to talk about basically how this starts making logic for us. So, basic diode logic. That makes sense? Kind of my process for today. All right. So to understand this, let's start off with everybody's favorite thing. Has everybody ever done any quantum mechanics? A little bit, right? So the first thing we always do when we talk about Schrodinger's wave is and we can write these little equations here, right? For Schrodinger. There's your basic Schrodinger wave equation in differential form. Like I said, we're not going to sweat this, so don't worry about it too much. Right? But we know how to solve this one. Right? This one it's a simple second order differential. Right? So we're going to end up with means and right? This is also why you end up having to have finite quantization laws, right? Because since you can only get sines and cosines for them, they have to match on their edges. So when you have orbitals, right, only certain ones are going to match on the edges. That gives you, that only certain of these are going to work, and therefore you're going to end up with a certain number of energy levels because your wave is proportional to your energy, equals hv. Right? So often. Anyway, this is the equation. I said this is about the only time I'm going to show you equation because I don't care. Okay? But I want you to know at least the basic idea that's out there. Now, this is going to describe how, right, where essentially that psi function is telling you what the formula or the particular function is that's going to be. If we square psi, it'll give you the likelihood that you find something there. This is where we're starting to get into the intuition. What does this mean? So psi squared gives us kind of you can think of it like a probability distribution. How likely is it there? Make sense? And we usually start off for a simple case with hydrogen. So it's an easy one to talk about because you only have to people so if you think about it, and let's go to even simpler stuff. How do I determine electric force between any two charge carriers? So we know it's really simple. Yeah, so it's got a relation between these. It's really simple to gravity, and this is why people often think, oh, there's got to be some way to combine them, because it looks very similar. Universal gravitation. G times mass 1 times mass 2 by something. So think about that, where it's going to be related to distance, but how fast does it drop off of distance? Right? So this is what we're calling English square law. Right? And in our case, we're going to replace the masses by the charges of the things we're dealing with. Right? And in our case, this will be 1.6 times 10 to the minus 19. Right? Don't worry about it. That is, Q1, Q2. Right? And we're dealing with electrons and protons, which have a unit charge. You can look up to 1.6 times 10 to the minus 19. It's fairly common. So feel comfortable with it at least. Right? And we're going to have a 4 pi epsilon, that's the other part of that calculation. Don't sweat this too much, right? Force from our charges is, right, Q1, Q2, right? I'm going to do this in two little pieces, 4 pi epsilon naught. But then we have this radius squared. It's also an inverse square law, how far away it is, right? from our terms, and it's a negative, right? But in essence, just think of this as a constant. I need the 50 numbers here. Yeah. Yeah, whether you look it up on Wikipedia, like I said, just remember the format for it. And as far as we're concerned, since these are fixed numbers, we're not, it's not like maths where it changes a whole bunch. We're dealing with electron versus proton, so they're unit charge. So it's essentially, it's always going to be that 1.6. Okay? Um, so just think of this in our sense as a constant, particularly for our hydrogen atom, which has one proton and one electron. And we're not dealing with isotopes or other stuff, but it won't change the charge anyway. So we're going to think of this as proportional 1 over r squared. So if you think then, let's think about what this is looking like. If we have our proton at 0, and this is kind of our distance, right? I'm just going to say R, right? What does this look like if I vary where my electron is? Right? It, it's going to get rid of, so it's not technically exponential, but that inverse square does have that similar kind of look to it. I agree. It's got a pole, because what is it when r equals 0? Yeah, right? Okay, so we kind of have something that looks like this on both sides, right? Because the square, right? So our force, the attraction between pulling them together is going to, in essence, like it's going to be a hole at that center, and then it's all towards 0 for the connection. Now, we usually talk about forces in here, but let's come to the attraction that keeps the electron hanging. How do I go from force to energy? And so I integrate. So again, we're talking big stuff. I'm not making it right. If you integrate the force, which we have an equation for, with respect to its distance from some R1 to some R2, that's going to give you what is the energy necessary to make that transition. So I'm trying to kind of build this basic physics, and it doesn't take too long to start seeing these cool properties. Yeah. Hopefully it'll start making sense and you'll remember them. So I can take this. What happens when I integrate this function? If I integrate 1 over r squared, what is we want to, so this is just, does this, the 1 over r is just, right, r to the minus 2, right? So if you just think integral this dr, forget about the limits and everything, right? So this is just power. And it always goes up 1, and then you have the 1, right? So there's some scale. But who cares, right? In essence, this is going to become a 1 over r. Yeah. So, like I said, right here we're trying to build a little intuition. So we're trying to get the shape of the curve. So I agree with you, it is a negative because, and in particular, we gotta multiply by the negative 1 because we're raising the power. But we already dropped the Q1, Q2, right? So it's proportional to, that's what I'm trying to say, right? So there are constants there, and we have to calculate it, know there are constants there. But sometimes we deal so much with the details, we don't understand the beauty of what the equation is telling us. So there are classes where that matters. I'm not having you build these, right? We want to use them, but we want to know why they work. To know why they work, you have to intuitively understand them. Does that make sense? So right now it's all about the intuition. But I agree with you, it's going to have a negative sign to it, right? So when we look at this again and we're plotting now the energy that's on, right? Again, we have to have some reference point. I have to go between two areas. And this is where we have to think a little bit about, I don't want a two variable plot, I want one variable plot. Right? When I'm plotting this, I would like to have R, but which one am I using? But if I do, I want to in some sense be able to look over some distance, so I want to be able to vary this a little bit. Right? So the question is, what are those two? If I have delta R, there's still an unknown reference point relative to it. Does that make sense? Right, so if we do delta R, I still have to, either have to give me R1 or R2 so that I can calculate that. I mean, because if you give me R1, I can do R2 as R1 plus delta R. That gives me a proper interval. If you give me R2, I can go from R2 minus delta R up to R2. But you have to give me something. Otherwise, I need a two-dimensional. So let me ask you, what do you think we should pick here? I need to pick a reference point that all of them are going to be plotted against. And hopefully it doesn't hamstring about that. So I could pick some arbitrary origin, right? But if I'm going to pick an arbitrary origin, first choices might be zero, right? But what happens to the function there? It blows up in your face, right? So do we want to pick the blow up that's top? Well, besides the kind of quote unquote center, the origin, what would be another natural spot there? Well, what if I go all the way over, right? Because I didn't show you where the units are, right? Because in some sense, that gets into all that scaling stuff. So if I pick some fixed point in space, other than one of the basic shapes of the graph, it's going to change around, and its properties are going to change, and be very hard to calculate. What happens to this function as it goes towards infinity? Is that easy? Yeah. Heck yeah, it's easy to get one. Could you get the two different ones and take the difference between them to get anything else? Yes. Yeah. You can integrate it up to from some R here towards infinity and some R2 towards infinity. I can get the difference by just the difference. So taking infinity is how you get infinite. So in some sense, our maximum on this is going to be out there, and we pick it at zero as our reference point. So everything we've got is going to be below the line. Because exactly like you said, there is a negative. So on any of these ones, the best I can ever get is zero. So when I draw this, this is just your kind of classic 1 over x curve. Again, it's got that same pole. It's not the best looking picture, but all right. We're going to this is G curve. So this is where the electron can take. There's only finite levels it can assume here. So the lowest state that it can get down to, this is where, this is a number that's actually good to remember, which technically it's minus, but the really important one is 13.6 electron volts. Right? That is the lowest state for an electron in a hydrogen atom. Now, the reason why this is important, this is actually what defines a lot of properties of physics areas. Have you ever heard about like ionizing radiation? Well, what's ionizing radiation? So typically we want to phrase it, we could do it as force, right? But we typically phrase it as energy. But there's lots of different positions out there in different mechanisms. So how do we distinguish them? So it's usually defined as the one that can take an electron from space state all the way up to infinity. So it's minus 13.6 electron volts. That is the definition point between ionizing and non-ionizing radiation. That happens to fall in ultraviolet. So this is why ultraviolet, you ever hear people say, watch out for UV rays? Well, this is why. Right? Amounts of energy falls. What is necessary to break an electron? Electrons can use weird bonding areas. It can damage your DNA, things of this sort, lead to cancer, because it can clear these up. So that's why I say the 13.6 is kind of critical, because it is one of those really important quantities. The next one up, just for interest, is minus 3.4 electron volts. Again, that's the next. Here's the important thing. If you're between these two, you can't go there. Yeah. So if you want an electron to go from here to here, it's going to get all in one fell swoop. You can't get more. It's got to get exactly the energy differential between them. That is a quantum. The electrons can fit in this case. Two. Why?
Because the KL1 only has its two available locations. Because they're based on vacuum.
Yeah, it's actually, but it's not just hydrogen that has those. Well, it's every energy state can only have two. Weird thing, right?
I mean, it still has to
So you're on the right track, but it's not everything has to have a unique quantum. Right? A lot of people do phrase it that way, but it's fermions. So there's fermions and bosons. We get the standard model particle physics. Right? Fermions, we have these kind of charges that's going on here. We're dealing with one of these, and essentially fermions have spin 1/2. This is the big differentiator. Where bosons do not have spin 1/2. Now here's the thing, if you're a fermion and you have spin 1/2, that spin creates some interesting things. You can now only have two fermions at an energy level, and one is spin up and the other is spin down. And that's it. Those are the only two. If you are not dealing with fermions, if you've got a boson, they follow Bose-Einstein statistics. And here, many of them is wrong at an energy level. So anybody ever hear of like Bose-Einstein condensate? When you're really, really cold, and that's what's getting really, really cold, you're dropping the energy. Why can it do this? Because under Bose-Einstein statistics, when you get really cold, there's no problem with them all being in the energy, same energy level. There's no spin. So you can get those suckers in really tightly, so to speak, and in areas so they can follow and get synced up on there. Okay, and that's basically what's happening with both Einstein concept. We don't really care about that, but that's a little fun. I want to give you that just to show you not everything is this. But the thing it is that spin, and we care about a lot of things with spin in engineering, particularly electrical engineering. We care about that. So it'll feel like everything, right? But it's really just fermions have this property. So it's actually, so direct, we all heard that name before, actually coined the name, and it's after Enrico Fermi, who was a physicist from Italy. You ever hear of back of the envelope calculations? That's Fermi. So Fermi is a famous physicist, and he's done a lot of cool stuff. NVIDIA actually named Hawaiian GPUs after Fermi because, Fermi did a lot of totally cool things in quantum and that. Plus some other fun stuff, things like that, which is actually quite helpful. Anyway, I digress. The important thing on here is we can only get two electrons in here. Think about it. We based on these, right? So if I've got an electron here, and if I want more, I get one more at this level, but if I want more than that, I'm going to jump up. So for hydrogen, if I've got my spin first, I do my spin down next, that's not too expensive. But if I want to add a third electron around here, I drop it into this area, there's a pretty big energy gap there. So this is how those band gaps form. It's based off of these energy levels. I don't get two here. I think it's got how does band happen? Because I can only hold two things. We're talking about bands. So let me explain how a band happens. Yeah, what band's electron is what?
Rails electrons, the outermost ring.
My band, so I have here,
You're gonna take it to something.
right? So my next electron is fairly cheap, it's nearby. And for that is the gap with, 10.2 electron volts, right? But that's a pretty big gap. That's actually the band gap. You're going to have a whole range in the same area. So the question is, how is the band?
How do you get back?
Any
Uh,
any bands. These are values, they're not bands. So a band is actually because we get a whole bunch of layers really close together. But we haven't explained how we get a whole bunch really close together. If they're too close together, spin up and spin down. But that's not a band. So how do we get that? So let me explain it. This is one of those things that you can't explain well. Even my physics course and that, they didn't really get into this. This is the easiest way to explain this. We've been thinking on this for decades. And it is absolutely correct on what's going on. But it just cuts through a lot of the denser stuff. We have to read a lot of equations. Let's take two hydrogen atoms now. All right, here's our zero reference. We're still going to use energy in this direction, but now I'm going to have two hydrogen ones. So I'm going to put these little circles here for their, right? I just made two little circles. That's my hydrogen nuclei, right? And for the moment, I'm just going to draw the vertical lines for a reference point. If I've got an electron that's, over here, I'm just going to put a minus charge and give some location. Right? If you think about, we know in the energy terms on this one, it looks something like 1 over x, 1 over x. Right? So we could say it's here, and I know what the energy must be at that point. It's there. And let's just say, for the sake of argument, I'm not saying I'm a great picture drawer, but let's just say this was our, minus 13.6 EV point, right? Again, I'm not trying to draw scales or anything, I just want to say, okay, let's say it's in that lowest state at this particular point. Is there any attraction to the other nucleus?
yes, there's some.
There's force on both, right? So in some sense, you can kind of picture that this one also, has its energy curve that's on it, right? And it's going out to zero in those directions. So, relative to that one, it's kind of way there. Now, if you were to look at this, take a look at the plot of what is the electron moved out, right, further away, it'll go to different points. Eventually, it kind of reaches this point, and it ends up more in the other. So now we can see how we all these electrons can get shared. Okay. Trying to get electrons out of there. And we take 13.6 electron volts. That's a lot of energy, relatively speaking. That's huge. When you add it up over a whole bunch of them, that's pretty big. But to get it 2, 3, right? But to go between two atoms, it's a little bit lower. It's not all the way. to spending the energy out here. There's no energy. So it's slightly cheaper that one there. Okay, what happens if I now move them closer to each other? Exactly. So I start moving it closer and I start seeing this happening, right? So the energy necessary to jump between them drops. And I can move them even closer. What happens if I move them this close, right? But they both have the same energy, don't they? 13.6. So what happens? Ah, they share. How many electrons can you fit in it? One thing here. So how many do you have in a particular ratio? Two. It's the Pauli exclusion principle. For spin, you can only have two. How many can you over here or over here? Two and two, then. So I have four, and four, and close enough, two of my potential spots just disappear. And so there, two, three, four. Where did they go? They go. So that understanding is not completely right. So this is where we have to add in. It's not totally classic. This is where I want you to get the quantum understanding, because these are going to bifurcate and split. And it's this process of splitting and spreading the energy levels out that's going to actually give you your bands. So as we do this, they don't go together. They'll actually split, so I keep all four positions. Let me show you why. Okay? This is where I was saying I need the idea of psi, and the fact that psi squared gives me a position. If I think about for a sec, let's just go back to a basic spot and I say, here is my electron. All right? It is my electron. So, yeah. Okay? Now, if this is position, and I just want to consider, for instance, this is kind of at the dead center, let's say, for the sake of argument, and this is my side. It could be a side, it could be a there's different. Let's just say that my particular function satisfying this looks like this. This is my side. That's the particular. Now that tells me that psi squared, right, is going to actually be the crucial part for this, right? And psi squared, that's our position area. So let me do one more here. All right, here's my electron. And if we considered psi squared, it's just going to look like this squared. So it's kind of going to go like that. It kind of pulls in. If it's less than one, it goes down. If it's more than one, it goes up. So you kind of get this, bell-shaped curve type of a shape to it. All right, and this tells you, right, our position. Now we know by Heisenberg uncertainty that you don't know the position exactly, right? There's position and momentum, right? And so in particular, right, the delta of your knowledge of the momentum, delta P times the delta of your position, delta X, has to be bigger than or equal to H bar. But don't sweat that. Right? We just know we can't know is that just a statement of how badly we measure things? We get better in the future and that'll go away? But is that caused by the fact that I think that's all the Yeah, it's actually very, so I even heard physicists explain this wrong, so let me be very clear on this one. It has nothing to do with how you observe. It is that you observe. And even more specifically, There is not an exact position. I am a very strong Christian believer, but I will tell you this, God does not make the exact position and velocity of a particle. Okay? Because there isn't an exact position. It would be a lie. You can actually see this. Has everybody seen 48 transforms? I can do it on space, right? So if you think of position, and if you think of, right, if you're considering like time, you get 1/time is your frequency in some sense. That kind of, in a sense, proportion to momentum, which is taking position over time. So you've got those kind of two quantities. If my distribution, whatever it is, in my space-time area shrinks, so I know precisely in frequency, 1/time, it's great. So, right, and if I shrink it in frequency, what happens in space? So what you're seeing here is a fundamental relation, mathematically speaking. If you know one more, you know the other ways. Because it just is. How do I solve a particle? It doesn't have one velocity. It's got different velocities at different places. Imagine some object and it's spinning and it's whatever, and you want to stop it exactly in time to find its position. Well, what's the velocity? Well, it's all kinds. There's a distribution of velocities to achieve that. Right? What if I wanted to know its exact velocity? Well, you have to measure it at 2 points. Spatial position. This has nothing to do with your technology. It literally, it's not there. It's the triangle inequality. Right? It is exactly the triangle inequality. So you can get Heisenberg just by doing master triangle inequality. That's why you can say God has a book and God doesn't. Right? Because God doesn't do false things. He would never lie to say, I know something that's not true. It's just, if it has an exact position, it doesn't have velocity in expression. It's a trade-off in physical space. Does that make sense? Okay. So when you're looking at this, this is a distribution, right? If you were to observe it, it would be a spot. But if you don't observe it, it all goes. And these are probabilities. Does that make sense? Okay, so this is in essence what that wave function is looking like. Right? So now when we think about this, right, and we're trying to get these positions off them, these probabilities are going to add. We take two wave functions, the wave functions will add, and we can calculate those probabilities off them. Right? So taking a look on these, as I am bringing them together for these, there is a wave function for one and the other. Now, this wave function gives me this. What happens to this wave function? Gives you the same thing, doesn't it? Because when you square it, the minus sign goes away. So this is whether they're in or out of phase. So when you take these two, right, and I'm merging these potential states, one from the green here and one from the blue, right, how do I know which one of these shapes I have for them? Well, when they add, I could have from one this shape, and I could have the same one in phase from the other. And as I bring them together, right, the orbital shapes for them, they're going to merge. And this is for the psi functions, right? So that means as they do, and they start overlapping, they'll add, right? So you'll get something in between higher, right? And as they get closer and closer, right, it'll overlap more and it'll start going up above. When you square it, when they're both in sync, you're going to get something that looks like that. So the probability is higher that it's towards the center, right? Closer to the nucleus. But what would have happened if they were not, right? That these were the two psi functions. Exactly. When they overlap, right, you'll get this, right? And as they get closer and closer, right, it'll get more and more. Well, when you square this is getting near zero, you're going to get something that looks like that, kind of. And this is the center, so it has to move, the probability moves out. But the closer you are to the center, remember we just calculated this, the more likely you are, that's a lower energy state. So this is a lower energy state. This is further from the center where the nucleus is. It's a higher energy state. The states have to bifurcate. That's what you notice. That is the bifurcation of the states. Well, what happens if I don't just do two of these? What if I do four of them? You're going to get more destruction or more building, so I'm going to get more states. And I could get, two that build, two that destruct, I can get all three the combos. Three that are on the same side and one on the opposite, I can get all kinds of combos. So when I start adding them together, I'm going to get all kinds of different energy levels when they build up. So what happens is the more of these things you have together, the more it's going to split. Now, how much can we pack together? We've been talking hydrogen again, but let's now think silicon, right? So when we think about this, if I have 1 centimeter on every side, we're going to ballpark maybe a half maybe silicon atoms I can squeeze and say 1 cubic centimeter. In that ballpark range, yeah, I can get about 10 to the 22. It's pretty good. Now, people need now the energy levels smashing in from it. Each one, they make these little fine gradations. So you're going to have a whole bunch of these complicated states that are in there. That's advantage. Because they all have to split away the Pauli exclusion principle, which you can see graphically happen as we start adding or subtracting on that. That's where advanced. It's completely understandable if you understand force and the fact that there is uncertainty. You add those two things in Pauli exclusion, the bands have to form. Now all of a sudden you can explain bonding and all kinds of other cool stuff. Right? We're bringing up stuff together, though. Right? Well, they won't do this application, but you get this little thing. And technically speaking, it's not continuous, but they're so close together, it's really darn hard to measure them. So it's basically, we just treat it like a whole. And that's happening with all these other areas, right? So we just kind of showed this for one at the 13.6, but realizing it's doing the same thing at the next one. So you get a valence band, right? That's done from the 13.6, and you get a conduction band, and that's from the 3.4 as you let those, and it will be a band. And you're going to take the lowest energy one available to you. Together. Now I don't have to get them all the way out. Remember, the energy to jump between them is that this is just kind of giving you that idea of how they fit together. Does it make sense why these properties happen? I hope it's starting at least intuitively. You can kind of see why there has to be a band in these things. Why do they have to be up? So now when you think about in terms of energy, I don't necessarily have to draw all the spatial components. We usually just draw this as an energy band, right? And we say, here is a region, we call this the conduction band, right? That's one of the upper ones that kind of split and form a whole bunch. And it's made up of, right, tons of little energy states in here. It's got 10 to the 22 of them for certain. So you might as well just consider it a continuous region, right? And then I have a valence region which is from all those top electrons, and it's all split apart. That make sense? Now, there's a gap between these. If I'm dealing with the valence band, right, is not full. So what's the difference from one of these to the next? Is really close. That's essentially why all you have to do is point something to the next high cycle. Well, when that bandstand is full, or your next one is up here, and now you have a big energy gap. And depending on how big this gap is, if it's really big, and the bandstand is full, guess what? You're an insulator. What if the big band isn't full and those two, in essence, are now going to create free space between them? Sure, it's really easy. If this thing is smaller, here's that, and silicon happens to fall in that range. Now, what you in essence need between these, right? There's also some thermal energy. So Fermi comes back. There's this thing called the Fermi energy. And this kind of for all the thermal stuff, how much energy is available. So that Fermi energy is kind of available energy. Some electrons, they can't have that thing. There's nothing there to go to. So some will have more, some will have less. So this becomes the probability that an electron gets propagated on to the next line. It's always somewhere between the last electron base state and the next one. And if you raise the temperature, you get more Fermi energy, and in essence, it's conductive. That's why at higher temperatures, it's easier to conduct electrons. Makes sense? So then you have a pretty good idea what these function. I believe we actually out of time, so I'm a little bit behind schedule, but I'm hoping this is starting to make sense the underlying why. Because if you understand why, everything we're going to build will just make sense. So we'll finish out, we'll build transistors, we'll show how diodes work in the next time. So we'll be a little bit on those, but I've got packed through them, so I'm okay. Any questions so far? Fine. Let me know when you're coming out if you're like, yeah, I didn't understand you at all, or that was good, or help me clarify this, so I can clarify the next time. Good? Awesome. Have a lovely day. Because then I'll try to get this uploaded as soon as they make it available to me. Sure.